Good morning. I repeat Mary D's congratulations for all of you to have arrived here. Particularly, I think we need the folks who came from those faraway places need a little hand for their journey. So I'd suggest we put them together for everybody from 10 foreign countries. Okay, so I'm going to talk about cognitive computing today. Obviously, it's been the topic of one of the two or three different kinds of tracks here. And many of you have participated, and so I hope not to be too repetitive for some of those who have enjoyed the discussions in the cognitive computing track. But I think for a lot of us, cognitive computing, it's a little unclear where it fits into sort of a broader picture of what we're doing in technology, information technology, and sort of the transformation to digital business that we're all going through. So today, just a quick look at the roadmap that I have in mind is I'm going to try to establish a context for cognitive computing and why and how it's emerging now in the conversation in business organizations. And then I'm going to talk a little bit, share some facts and research about how people view generating value from cognitive computing. And then perhaps belatedly, I'm going to get to the question of what is cognitive computing anyway? And hopefully, by the time you leave here today, you'll have a better sense at least of the perspective that we've been evolving at the Cognitive Computing Consortium. And then I'm going to share with you a cognitive application framework, which is designed to help executives and business managers understand what they're getting into when they start thinking about doing something with cognitive. And then I'll close with a kind of a brief view of talking about threats, risks, and ethics involved in cognitive and AI. And this could take a whole other keynote, a whole conference to cover these topics. But hopefully some of you were able to join the discussion at the end of the day yesterday that I had with yesterday's keynoter, David Weinberger, my old friend and colleague, and also Sarah Mattingly-Jordan from IEEE and Virginia Tech University. But if you were in that session, you know that it's a lively topic and you could talk about it almost all day long. And the press is actually doing a very good job talking all day long about it, particularly as it involves current events. And I'm actually going to touch on that a little bit too. So without further ado, I thought given that it's early in the morning, I thought I'd do a sort of a comic book version of where we've been in data and information technologies in the last, let's say, 15 years. And I must say the 800-pound gorilla that is not in this slide is the internet. The fact that the internet happened and suddenly there was a capability of generating a volume of data that nobody had ever really seen before. And that gave some smart people the idea that maybe this new tool that was causing such problems could be used to become part of the solution. And so here came cloud computing in the upper right-hand corner there. And I think cloud is really responsible for a lot of what we've been seeing evolve, particularly in the last decade. So if we go down to so this journey has gone from the cloud to then understanding that big data was part of everybody's life from here on out, and that it had lots of different components, including unstructured data, including log data from various sensors, IoT sensors, including text analytics kind of data, parts of speech, tags, and suddenly one document could have 1,000 data points. And so this is all contributing to a sort of a crisis in the database world, because SQL databases or other kinds of traditional databases, as you all know, pose a lot of challenges if you're trying to store unstructured data and tons of log data and pictures and videos and all the kinds of data types that people weren't necessarily used to using on a day-to-day basis. And so what came along, moving over to the lower left, was the idea of non-SQL. And sort of appropriately, the company with the biggest problem, Google, came up with the idea of, well, maybe we can have a sort of an unstructured data area, not totally unstructured, but we'll call it Hadoop, and we'll say you don't have the same constraints when you use this type of data repository as you do, particularly constraints handling all these strange kinds of data, as you do with the traditional systems. And that gave rise, moving up to the upper left quadrant, to the whole idea of data lakes. You probably can't see this, but that ocean is made up of ones and zeros. And that's probably the way a lot of people's data lakes look to them right now, is a turbulence of ones and zeros. But at the same time this is going on, we, on the management side, more the human side of things, another bunch of smart people realized that with more and more digitized information in the organization, decision-making should really modernize and go from being shoot from the hip, and everybody's sort of intuitive, executives making decisions on their intuitive sense of what they'd learned over a 30-year career. Now you could actually make a decision based on a quantitative data. And so those of you who were in the track on competing on analytics yesterday will remember that Tom Davenport, one of our colleagues at Babson, I'm going to talk about a joint research program that we have going with Babson College in just a few minutes here. But Tom Davenport, who is at Babson, wrote a book about more than 10 years ago called Competing on Analytics. And at the time, he was hard put to find a lot of examples of companies who were competing on analytics. And the examples tended toward Las Vegas casinos, for example, or baseball teams. Moneyball, the book Moneyball had just come out, and the idea of tracking the statistics of baseball players was brand new. And so now we know, of course, that it's become, in that decade since that book was published, it's become mainstream to be making decisions based on whatever the decision area is, based on the set of data that's available. And so many companies have really invested in building up their analytics capabilities. And many of them, of course, would love to say that, as it says on this slide, that they have prescriptive analytics and predictive analytics. But the reality, of course, is that many companies are only doing diagnostic and possibly descriptive. Just get a handle, get data that describes what we're doing. And then, if we're lucky, we get analytics that really give us a good idea of how to diagnose issues and move forward in a smarter manner. But this also brings up now what IBM had in mind. And I give IBM a lot of credit for introducing the world to cognitive computing in 2011 by building this Jeopardy-playing deep blue kind of system that could actually perform what we call open domain question answering, or pretty open domain question answering. Which, for those of you maybe not so familiar with the natural language world and text analytics, open domain means that you don't specify in advance a particular area, like some area of physics or some area of historical research. Because if you specify in advance an area, then a human programmer can pretty effectively create a system that will understand all the words in that particular domain and be able to help a human being get, answer questions that they have about that domain. But if you open it all up, now the human programmer is kind of at a loss, because you can't boil the ocean. It's like sort of a Wikipedia problem, and this is why a lot of early text analytics demonstrations, or companies who were building text analytics platforms used Wikipedia. If we can do question answering against Wikipedia, we must be really great. Well, IBM took a true leap forward in Watson by integrating a whole bunch of different kinds of technologies, including the most advanced text analytics systems, but also by doing statistical and probabilistic evaluation of answers that were coming back, because I'm sure many of you remember that in Jeopardy, a wrong answer counts against you. And so you don't want to answer too quickly and give the wrong answer. So in addition to generating answers out of many, many kinds of domains within the Jeopardy game, Watson was doing a whole bunch of probabilistic evaluation on it. Watson also had to integrate a hardware system so it could press the button to, you might call it a rudimentary robot. So because Watson the machine the player had to do the same thing that the human player had to do, which was decide on an answer and press a button if you want to, articulate the answer and hopefully win that round. So anyway, I give IBM a lot of credit for taking on this very complex analytics problem and convincing the world that maybe it was time to think about these systems doing more. Because, of course, most of our experience with computing systems are with deterministic systems that you know that the system is there, for example, like an accounting system, to show you exactly what the net income of the firm was in that quarter. So you know exactly the question you can ask it and exactly the answer you're going to get back. The thing with cognitive computing is that you don't know what the question is going to be, and you really don't know what the answer is going to be. So this ushers in a whole new era. And incidentally, it's also linked to the data lake that we were just looking at, because there's now too much data in all of these domains that I was just talking about for human analysts to be able to work through a lot of these repositories in any kind of efficient time frame. So suddenly we're talking about cognitive computing. And this is a slide from a Deloitte University press training materials about cognitive computing. And it has the big I, you know, this is a kind of an AI flavor thing. And it also has all these honeycomb hexagons, which have become very popular because every system has so many elements now. One way to put them together is a honeycomb, and I must say I like this kind of treatment, but I also kind of laugh that we can't come up with anything better. So at the top we have, I basically share this to show you the variety of things that people are thinking about. So Deloitte identified computer vision at the very top as an element of cognitive computing, machine learning, natural language processing, optimizations, here we are back to analytics again, planning and scheduling, I'm not sure about that one, robotics, which is sort of part and parcel of the AI movement and has been part and parcel of the manufacturing industry for many years, actually. Rules-based systems, there's still a place for humans to create rules and get good results. And speech recognition, finally, on the far left. And so this kind of led us to think about, well, we ought to have a Wordle or, you know, a word cloud to sort of lay out what's going on in this cognitive discussion. How do we talk about it? So my colleague, Sue Feldman, got our let our fingers do the walking and created this one, which you'll see. The thing I want to point out is that we have cognitive computing on the left and we have AI on the right. Because going back to IBM just briefly, in the terminology wars, IBM created cognitive computing as a major marketing theme right after the Watson Jeopardy victory, and talked about cognitive computing as the next phase of enterprise computing and how people should get on the bandwagon and start thinking about how to do this. Nobody else was talking about cognitive computing, and nobody else was talking about AI much at the time. Now we're talking 2012. And IBM, I told Chris over here that I would not, you shouldn't take this wrong, your next speaker from IBM. But IBM didn't dare use the word AI, because AI, even at that time, was a soiled name, so to speak, in the marketplace, because we'd had an AI revolution already in the mid-'80s to mid-'90s. Billions of dollars were poured into new companies developing AI techniques and developing AI computers. Many of those dollars went to Cambridge, Massachusetts, right across the river, where companies like Symbolics and Kendall Square Research and Thinking Machines built whole new specialized computer architectures to handle the processing loads and the different kinds of issues that come up with trying to simulate in a computer the sorts of things that you can do in a human brain. So so we then got very confused, because then Google and Amazon and Facebook and many of the newer technology, what are now considered the technology behemoths, started talking about AI and about how they had AI labs, and they just hired 1,500 AI researchers, and that we were going to take over the world with AI in some manner. So IBM, sure enough, by 2016, IBM was starting to use the term AI, and in 2017, they really used the term AI. And so now everybody's talking about AI. So why are we still talking about cognitive computing, you might ask? when we have cognitive on the left, we've got all these things in the middle, and we've got AI on the right. How do these two things come together? So this is what we propose from the standpoint of our consortium, that the fundamental differentiation is the extent to which the machine can emulate human thought processes, behaviors, and interactions. So on the left, under the AI umbrella, we propose that only fully autonomous systems should be considered in the realm of AI. Now, almost no system that you've heard recently tagged AI is a fully autonomous system. And we'll get into this a little bit more. But then, and the machine under the autonomous model, the machine is literally doing the work of the human brain. No human brain need apply. That's the meaning of autonomous. And then the machine is literally put in the position of being an author of its own actions. Now contrast this, moving to the right, to the gray area. I don't think, did we think about, Sue, you can probably help me out, did we think about gray matter when we were saying, when we did this? Anyway, on the right, under the cognitive column, the machine behavior is dependent on the human, the gray matter of the human that sets up the machine. And the machine is an information tool. And it's an agent of some business process or some intention of a human being. And it becomes more like an assistant than an independent actor. In fact, it is, well, it's not necessarily an assistant, but it very much can be. So given that there's this terminology, I mean, we think that this is a clear way to think about it, but in the market in general, there's a real confusion around the vision of AI. What is cognitive? Do we even think about cognitive anymore? And so that leads to the period that we're in now, which I'm referring to as the early chaotic era. And that's because we have confusion from multiple vendor interpretations. We're missing trusted resources. This is credible guidelines and information are in short supply. That's one of the main reasons that we founded the Cognitive Computing Consortium. The skill sets to deal with these technologies are in short supply. We're missing the cross-silo networks of people actually within organizations, because the technology group and the manufacturing group, or the technology group and the marketing group, or maybe all three, should be talking to each other in ways about these cognitive, I'm going to keep calling them cognitive applications. And they need to be able to talk together in order to generate the kinds of decisions that would be made if a human committee from those groups were to make such a decision. And then there's very much uncertainty about AI, ROI, how are we going to actually make money out of these things? Most applications today are either prototypes, and as such they're highly customized, or they're barely in production and they're still highly customized. So there's no sense of an industry standard, even customer support application, for example. And the terminology is unsettled, which I've obviously made a big point about already. And there are no industry standards across many of the areas of the field. So, chaos. So how do you get value out of chaos? So last month, McKinsey published what I think is an excellent report. And if those of you who are familiar with McKinsey, just go to mckinseyglobalinstitute.com and you can download this thing. But they projected that the potential value of adopting, they call it AI, is like 3.5 to 5.8 trillion annually, globally. Now that's a big number to me anyway. I don't know what your pay grade is, but that's a big number to me. So, and they did it in a very responsible way, I think. They identified 400 use cases, individual sort of AI or cognitive applications across an enterprise. They looked at 19 industries, and they looked at 9 different business functions. So this gives them a level of granularity in thinking about, well, what is the potential economic impact for an improvement, an adoption of new technology to help with this particular business function in this particular industry, this particular one of the 400 use cases. And so an example of the kinds of output that is in this report, I'm not sure how much you can read of this, but this obviously is a ranking of the industries on the right, with the blue histogram bars, of the industries that would benefit the most. And you can see travel's at the top, and aerospace and defense is at the bottom, and everybody has a different level. I wanted to focus, though, on the vertical bar to the left, which is labeled the breakdown of use cases by applicable techniques. And the big blue bar in the bottom of that overall display is AI can, I can't even read it here, can improve performance over that provided by other analytics approaches. And that's most of the applications. So AI is seen as a augmentation, so to speak, over what can already be done with analytics. And then just above that in the turquoise is 16%, I think it says, where AI is necessary to capture the value. And on the top one, 15%, a full value of improved analytics can be gathered by just improving techniques that we use today. So I highly recommend this report. It goes into great detail about all of its the areas that I've just been talking about and more. And by the time you're done reading it, you're thinking, well, 4 to 6 trillion might be a number that might actually be true. Now, another approach of looking at the market is, or the value in the market, is one that IDC takes, which is to say, how much spending is going to happen in the area of AI. And the spending is mostly built up out of the sales of software and various kinds of services to by vendor companies to enterprises. So IDC is projecting $18 billion of spend this year, growing to $52 billion in 2021 for a 46% growth rate. So IDC is very much anticipating a rapid growth in spending on this type of technology, which I guess is a way of saying that if you don't see it in your organization today, by 2021 you probably will. So let's shift gears for a minute now and get away from the market numbers and talk more about what is cognitive computing anyway. So in 2015, at the Cognitive Computing Consortium, we gathered a working group of about 25 industry experts, I would say, from academia, from vendor companies, industry companies like IBM, for example, and also consultants and some enterprise people, sort of enterprise innovation managers who are looking at these problems. And because we wanted to come up with some sort of definition that could stand the test of time and not be flipping back and forth between cognitive and AI, and generally following the pattern of the media and the press stories that were going all over the map at this point on what these things are. So what we came up with, the big headline is it makes a new class of problems computable. And that's basically what we're pointing to, is that we're talking about trying to take the wetware up here, the gray matter, and turn it into a machine application. So that's the first part. That's kind of the intention and the goal of cognitive computing. And how do we get there? The most important thing is that cognitive systems can make context computable, which is something that traditional systems are miserable at, because typically they only have their own context. They're built with a context. They can't think outside what has already been put in them. The cognitive system is just the way we do when we're in a traffic jam on a country road because of a pothole problem or an electrical line problem. That's one context. When we're in a traffic jam right out here on the Southeast Expressway, that's another kind of problem. In the latter case, we know we're going to be there all day, and in the first case, we know the guys will get out of the way and let us pass in the country. So context is critical. And the other element that we thought was critical was that cognitive computing's applications change the nature of the relationship between the human being and the computer. Because suddenly the computer, rather than being strictly an inanimate object, is more like an assistant, more like we are in a conversation with this thing. for better or worse. And we see the sort of the beginnings of this with Alexa and Siri, and I'm sure other, you're familiar with the sort of rise of different kinds of systems that hope to be able to maintain dialogues with people. But this is only kind of the tip of the iceberg of where we're going over the next few years. So quickly, 5 sort of pillars of this area. In other words, what is it that makes cognitive computing particularly unique? And first of all, we're saying that these systems learn and they adapt to changing data over time. Obviously, the core of this at the moment from a technology perspective is machine learning and deep learning and various kinds of statistical data science-oriented decision processing that we're, many of which we've been familiar with for a long time, but kind of transformed into a more conversational, more persistent kind of set of things depending on the kind of application we're trying to build. They're probabilistic. They're statistically based. They come with a confidence ranking. They're not coming back and saying this is the answer. Just like Watson in Jeopardy would inside Watson's brain, he was saying, well, if I say yes, I've got the answer to this, I've got a 87% confidence rank on this thing that I'm going to say that the answer is the, Buckingham Palace or some sort of weird thing from British history, or whatever the answer would be. So you may not get the same answer twice in a row, depending on what the context is and what the confidence score is of the machine. It's contextual, I just talked about that. It's conversational, I've mentioned that. And a high degree of integration is required, both on a software level and on a systems level. That is to say, the manufacturing system and the marketing system and the innovation office may need to start sharing data and integrating information out of their systems in new ways. So why are we going to all this trouble? We've had these perfectly good systems that give us answers that we can depend on more or less, although we know we have had garbage in, garbage out, but maybe we can figure out which ones are garbage and which ones aren't. But why are we getting into this, and why do we call it cognitive? And I'd like to share with you cognitive processes. This is literally right out of Wikipedia. This is a kind of a psychologist or cognitive scientist's view of what is it about the brain that makes us talk about cognitive capabilities in a different way than we talk about a lot of other things, about the way our bodies work. And here they are. They're the ability to pay attention. They're the ability to form knowledge. They're memory, the workings of memory, both long-term and short-term. There's evaluation and judgment, reasoning, problem-solving and decision-making, and communicating through language. So, if you think about your laptop, you may ask yourself, well, how many of those things is my laptop actually capable of supporting today? But so to make this a little bit more real, I thought I'd share an example. So this is one of probably the most popular cognitive application that companies have tried. It's one of the easiest ones to program, and it's an area of most enterprises that's deeply in need of incremental improvement, shall we say. So we want to have a customer support chatbot. So we have a little Star Trek-like guy up there in the right-hand corner. I think it's a guy. And let's think about what this chatbot has to do. If it's going to pay attention, it needs to respond to the user's inquiry. Duh. But what if the user's inquiry is like it's going to sing me, the user's, imagine, hum a few bars and I'll fake it. So if you're a radio, Spotify or Pandora or one of these services and you want to provide a customer example, maybe the user's going to sing a song, and I think the chorus goes like this, and I'm supposed to return a real song or tell the user how to get the real song. And that's an extreme example, I'll grant you, but nonetheless, even on a simple example, the computer has to understand the terms that I'm using to speak with it or type to it. And then it also has to be able to Well, we'll get into this in a second. So after attention, we have knowledge formation. How well does the chatbot understand the user's question, which is what I was just starting to talk about. And then what about memory? I mean, has this chatbot spoken with this particular user before? And what were we talking about last time? And does it sound like this user is coming with the same problem that they had last time, or is it maybe a different problem? But maybe the different problem shares some sort of core issue, like the user doesn't know how to right-click and get the music to play properly. Maybe I can suggest, right-clicking again, because it worked last time, even though the problem was different. So that is a matter of evaluation and judgment on the part of this chatbot. And then it has to reason about what kind of matches for the user problem is available in the support materials that it has, whether it's product manuals or, histories of all kinds of interactions with similar kinds of users in the past, all the data that the customer support chatbot has at its fingers to be able to analyze. And then, the chatbot has to make a decision. What do I propose? First of all, which matches look good, and then, like Watson and Jeopardy, which ones do I have the highest confidence level in? And then how do I communicate? Back to the sort of the final cognitive capability. How do I actually communicate with this user? Is the user typing at me? Is the user singing to me? Is the user, how have I been set up to do this? So many of you may know, how many of you have had experiences with chatbots either in your company or okay, so quite a few. So I don't know how many of you are happy, but there have been a lot of not so great experiences with these efforts. I would say chatbots were incredibly hot beginning in 2015, 2016. By 2017, people were really starting to get dubious and skeptical about whether these things could actually take over from people, and if so, how. And there had been some tremendous disasters, of course, like Microsoft Tay, which had been, supposed to be a friendly chatbot that I'm sure you all know was turned into a raving misogynist and racist in 6 hours or something by people sort of spamming its interface. So that's an example, but basically every cognitive application has to be thought about with that sort of background in mind. How are all the cognitive capabilities going to be brought into play? And what are really the requirements that the machine is going to have to meet in order to make a successful rendition of human cognitive processing in the context of this application? So, speaking of the context of the application, we set out at the Cognitive Consortium to do some research into how we could help executives, line of business managers, innovation people, all the people who are going to have to make a decision about a newfangled AI thingy that was going to come in and solve a problem in a particular area, whether it was customer support or manufacturing, increasing manufacturing yield or whatever it was going to be. How do we think about, how do we suggest to executives that they look at developing these things, and what would be some helpful mental models that would enable people to make better decisions? So we started to work with Babson on developing this, I'm calling it a machine intelligence framework here, because as you see, we wound up figuring out a couple of fundamental trade-offs that could be graphed in a simple 4-cell array. And this horizontal axis is the gradient between augmented intelligence, which I've been referring to as cognitive computing, where the human being is in charge, so to speak, to autonomous intelligence at the other end of the spectrum, where the machine is basically in charge. And we call this the modality axis because it refers to the machine's ability to render human behavior. So the other axis is more, what is the character of the application? What is its intent? What is its purpose? And we're proposing that there are two fundamental purposes. One of them is discovery, where the human is really does not know exactly what to look for, is looking for help in discovering something new about a problem area or about any kind of situation in which they do not feel that they have any inkling as to what an appropriate answer would be or an appropriate source of action would be, course of action would be. And that's contrasted against advisory applications, which are those that the user knows that there is an answer to it. They just need to have the machine bring the answer and the right answer as quickly and as efficiently as possible. So this is the basic framework: advice versus discovery, augmented versus autonomous. And here's a similar layout, but a completely different approach, because this graph, this quadrant, is about the extent of human understanding. This is classic knowledge management. Any of you who went to Knowledge Management 101 should know this by heart, because we still have the discovery applications versus the advisory applications. But now we're talking about how much do we know as opposed to the autonomous versus augmented. How much does the machine, how much can the machine work like a human? Now, in this representation, we're talking about how much do we know, and what are the application requirements of what I'm looking to accomplish relative to what we know. So this is the known, arraying the known versus the unknown. So in a situation where we have known knowns, in other words, the user comes to the computer and says, I know there's an answer to this problem, and I know that it's been documented in many places, I just can't find it, so get it for me. So if we were building a cognitive application for this type of knowledge problem, we want fast, accurate, efficient retrieval of the answer. On the other hand, at the same end, the advisory application end of this model, there's this unknown knowns, and this is basically a matter of the user doesn't know that there's an answer, but the human race knows that there's an answer. And so in this quadrant, we're basically trying to make sure that bits of knowledge that are well known are not overlooked. So the idea for an application that needs to have this kind of characteristic, it's looking to minimize oversights. And then we have the famous known unknowns that Donald Rumsfeld talked a lot about during the first Gulf War in his briefings, talking about known unknowns, because they would know that something was going to happen, but they wouldn't know exactly what it was. And so the idea was to try to tune your prediction models well enough to enhance the discovery process and be less surprised by these known unknowns. And then, of course, the fourth quadrant is the unknown unknowns, and these are things that you didn't even anticipate. Now, they could create breakthrough insights, and you'd have new drugs and all kinds of fabulous new solutions to problems. Or they could be very much bad news and disaster happening and require first responders and crisis mode. But anyway, those are the four. When you take those together, we think that goes across the range of the possible application types. So here are some specific examples. And these are paired, I might add. So over on the augmented intelligence side, a discovery application could be that you were investigating a new job, changing jobs, and you wanted to look at new job areas. So you wanted to discover insights about what skills would be needed to apply for certain kinds of jobs that you found attractive. And below, if you look at that from an advisory perspective, let's say you had already decided which job area you wanted to look at specifically. What you then might want is advice from the system about what is entailed in getting a professional certification in a particular area. So at the same time, we have on the a more automated way, where these are moving to the right. You'll notice we don't have any applications to the far right, autonomous intelligence, because as I was saying, we don't know of any totally autonomous systems that do things like new drug discovery or provide an assistant to an oncologist. But these are specific pairs of both discovery and advisory. They're discovery advisory pairs, so that if you're exploring, you are looking for new drugs. If you're an oncologist, you want an assistant to help you decide what kind of treatment is appropriate for this particular patient. So enough of the quadrants. Let's talk about evolution. This is our proposal about what's going to be happening. You see on the left-hand side of this funny-looking diagram, we have systems that are driven by human direction and rules, and they tend to be, and as of 2018, we're labeling these traditional. This is the traditional system, and it's typically referred to as a system of record. Now contrast that with the far right of this rectangle, when as we move from augmented intelligence more toward autonomous intelligence, the systems become probabilistic. They are creating machine intelligence, or they're being driven by machine intelligence, and they become systems of insight, helping people, helping make real or make computable people's actual brain systems. So we think that over the next X years, there will be fewer and fewer of our traditional systems and more of these machine-directed systems. But the important point on this is that in the lower right-hand corner with that little ellipse, we don't believe that those lines ever come together. At least we hope not. Ray Kurzweil would say that the singularity will take care of that. But so another way to look at this is, what we're saying is that right now cognitive systems are kind of addressing a relatively narrow band of opportunity within the augmented, the computer as assistant mode. And over time, we expect them to be becoming more and more prominent, so that in 30 years, 100 years, AI, maybe we will have real AI systems that will be doing much more for our future generations than we can imagine them doing right now. So in the few minutes I have left, I'm going to go quickly to change gears again here and talk a little bit about the process flow for a cognitive application. I mean, how do you think about actually building one? And so what we thought was, this is not rocket science. You have to start with a business objective, a very granular understanding of what kind of business objective you have. And that's probably not increase quarterly net income by 3% for the next 8 quarters, because that's well, where do you start with that? But it could be create a chatbot that really is effective at helping our customers actually love interacting with our customer support representatives. And so maybe it's a customer experience focus, and then within the customer experience, it's, well, how do we deliver this particular type of system in a way that will make customers love us? And that kind of goes through specifically to the question of context. So we start with business objective, and then, unlike most systems, we put this processing block related to understanding context. And we've represented that, considering it's spring in Boston. This is our daffodil or daisy representation of what context is. But you see, the classic contextual questions, who, what, where, when, why. And we have to take all of these things into account, that a task or an activity that the user's working on, for a what, where, what kind of device are they using, where are they literally on a GPS system, who, what's the state of this user, is it a returning user, a brand new user, not a customer yet, how are we, how are we doing this, what business processes are being touched, and what data do we need to be able to manipulate? And why? Why is this user coming to us? What is the intention of our our business objective translated into intention about how to service this user, so to speak. So we could talk, again, a whole day about the different kinds of context, whether it's the semantic area, the domain, what kind of data. Data provides its own context or lack thereof. Security is a big issue. We can read emotions more and more, interpretation of emotions through video. There's lots to talk about context. But sensitive to time, moving forward, we have these next two green blocks are harken back to the two axes of the model, the purpose and the modality. So is the application an advisory application or a discovery application? Is it a augmented model, or are we trying to go for more autonomous operation in this particular application? And then we get to another big difference between cognitive application processes and traditional application processes, and that is behavior. And so we have another daffodil here around different kinds of behavior. Is the interaction going to be voice? Is the interaction going to be based on text? Are we going to be interpreting tone in the words used, whether spoken or typed? What kind of cultural sensitivity do we have? How many of our customers are international, are women, are Hispanic, are different kinds of cultural backgrounds, non-English speaking? Again, the behavior itself is context and demand driven. I mean, is somebody broken down on the side of the road? Is somebody using their cell phone from the metropolis? There are a lot of different things to consider in context. And so finally, we come to the bottom line where most people start, which is with the data that's available and the technology that can be used against the data. And what we're saying is that unless you understand the top 5 green blocks, you won't be able to select or integrate the data that's required to actually succeed in this particular cognitive application. Nor will you, and if you don't know what kind of data you're going to be using, you won't be able to understand what kind of technology you need to manipulate it. So I'm going to close with takeaways from this cognitive applications framework. Cognitive computing is a set of technologies that support a spectrum of uses. In combining these, designers must make trade-offs depending on the type of problem, the use, and the users. The framework itself offers a method for decision makers to define their problem and select appropriate cognitive computing investments. And the framework provides a logical step-through process for understanding and planning cognitive application projects. We believe that understanding the context requirements, data, technology, and behavior enables sound judgment about knowledge, skills, and abilities required for successful project teams. And I see that my time is just about up. I don't know if we're taking questions, Mary D, or not. We're not taking questions. So just to keep things moving along, I'm going to end the presentation here and keep the show on the road. Thanks very much for your attention.